Picture a modern metropolis. Roads, skyscrapers, utilities, and infrastructure stretching horizontally for miles. Now compress that entire city into one footprint and force every system to stack directly above itself.
Suddenly, the ground is thousands of feet away.
This is the Burj Khalifa, not simply the world's tallest building, but a city turned vertical. Its 163 floors force systems designed for horizontal cities to operate inside a tower nearly half a mile high. And gravity, normally a reliable part of urban design, becomes the enemy. So how does a vertical city this enormous deliver water, remove waste, survive the desert heat, move tens of thousands of people, and stay standing? It starts with something deceptively simple: turning on a tap. In a normal home, water flows almost instantly.
At the Burj Khalifa's summit, more than 2,700 feet above the ground, the challenge is not getting water there.
It is controlling the pressure required to get it there. A single pump pushing water from the basement to the top would create roughly 1,200 psi at the base. A household faucet operates around 50 psi. Even a powerful fire hose is around 150. At 1,200 psi, joints and pipes would face forces capable of catastrophic failure. So engineers abandoned the idea of one giant water system. Instead, the Burj Khalifa is divided into 7 mechanical zones, each serving roughly 30 floors. Water rises from the basement to a tank around the 40th floor. An independent pump then pushes it into the next zone, and the process repeats upward. But what goes up must eventually come down. Wastewater creates a completely different problem. A column of waste falling through a vertical pipe can build enormous momentum before reaching the bottom. Then it has to make a sudden transition from vertical flow to horizontal drainage. Without careful control, the flow can surge, overwhelm the pipe, and create pressure waves that push air and sewage back upward. In the worst case, toilets on lower floors could erupt under pressure. Engineers responded by making the main waste pipes enormous.
About 24 inches across, compared with roughly 4 inches in a typical home.
The extra width helps maintain an air column through the center, while the flow spirals along the walls. Collection points also interrupt the descent, dissipating energy before the waste reaches the ground. But then Dubai faced a problem no plumbing calculation could solve. In the mid-2000s, the city was expanding faster than its infrastructure. Skyscrapers were rising before the underground sewer network could catch up. For the Burj Khalifa's first 3 years, the world's tallest building depended on orange sewage trucks. Every morning, waste was pumped into tankers and hauled across the desert to treatment plants. A futuristic 163-story skyscraper was effectively relying on a fleet of trucks to perform a job its surrounding city had not yet been built to handle. Only in 2011 was the tower finally connected to Dubai's underground sewer grid. But gravity was only half the problem. The other half was the sun.
With temperatures reaching 122 degrees Fahrenheit, the Burj Khalifa becomes a vertical heat trap.
Above the 80th floor, residents can watch the sun set roughly 2 minutes later than people on the ground. Around the 150th floor, the difference approaches 3 minutes. Its facade contains 26,000 specialized glass panels, covering about 1.5 million square feet. Their reflective coating rejects much of the solar radiance can enter the building. But glass can only do so much. The tower's real cooling strategy begins underground. At night, when demand is lower, a basement plant produces ice slurry.
During the day, that stored cooling capacity is released as chilled water circulates through the building's climate control system.
At peak capacity, the system provides cooling equivalent to melting about 13,000 tons of ice every day. But Dubai's heat was not only a problem after the tower was finished. It was already threatening the building while it was being constructed. Concrete generates heat as it hardens. In Dubai's extreme temperatures, that heat can cause concrete to set too quickly, crack, or even harden inside the pumping system before reaching the upper floors. Engineers developed a custom high-performance concrete mix and added massive quantities of ice to cool it before pumping. Major concrete pours were also scheduled at night, when temperatures dropped into the 85 to 95 degrees Fahrenheit range. Once the tower was complete, the same desert heat had to be controlled every day. Now the tower has water moving upward, waste falling downward, and millions of square feet of glass fighting the sun. Then comes the problem of moving the people. A tower this large cannot operate like a normal building. With tens of thousands of people moving through it, elevators stopping at every floor would turn the entire building into a vertical traffic jam. So engineers designed the elevators like a transportation network. The Burj Khalifa uses 57 elevators,
including high-speed systems that move passengers directly to 3 sky lobbies on floors 43, 76, and 123.
From these transfer hubs, passengers switch to local elevators serving individual floors. But the transportation system is only one part of the tower's internal architecture. Its mechanical floors became critical choice zones throughout the tower. Major infrastructure is distributed through the building rather than concentrated in one location. That creates something more important than efficiency: isolation. If one system fails, the entire vertical city does not have to fail with it.
A pressure problem in one zone does not automatically disable every floor above it.
A mechanical failure can be contained. Major services can be separated, transferred, and maintained without turning one fault into a building-wide catastrophe. The same philosophy governs the elevator system. High-speed elevators handle the enormous vertical distances, while local elevators handle the final distribution. The tower does not depend on one continuous path from ground to summit. Everywhere you look, the same principle appears. Break the impossible problem into smaller systems. Control each one, then connect them without allowing a single failure to bring down everything else. And that is what makes the Burj Khalifa so difficult to engineer. Water has to climb more than 2,700 feet without destroying the pipes. Waste has to descend hundreds of meters without turning gravity into a pressure weapon. Cooling systems have to remove heat from a glass facade large enough to cover 1.5 million square feet.
Elevators have to move thousands of people through a building that behaves more like a transportation network than a conventional skyscraper.
And concrete has to be pumped upward while the desert is trying to make it harden before it reaches its destination. The Burj Khalifa is therefore not simply a tower with apartments, offices, hotels, and observation decks. It is a vertical city whose infrastructure had to be reinvented because the ground was no longer close enough to help.
Every meter upward increases pressure, distance, heat, travel time, and the consequences of failure.
So the engineers did something remarkably simple. They stopped treating the building as one enormous object. They turned it into a stack of controlled environments, connected by carefully managed transfers, protected by redundancy, and designed so that one failure does not become everyone else's problem. That is the hidden engineering behind the world's tallest building. Not height, control.
Would you live in a city built entirely inside a 6,000-foot tower? Or would you rather stay on the ground?
Tell me in the comments. I'll be reading them.